Still focusing on chapter 7, chemistry, first of our chemistry chapters. We're looking at part 2 right now. So the part 2 homework quiz will be due on Sunday. So what we're going to do this week with chemistry is we're going to be looking at and identifying covalent compounds and ionic compounds. We're also going to learn how to name them. So what we focused on last week was the chemical formulas and how to do calculations using the chemical formulas given the compound. So now we're going to identify the type of compound that we're looking at and name them. So to do that, we'll need the periodic table. So here's my makeshift periodic table. I have color-coded it so that you can see where the metals, nonmetals, and semi-metals, or metalloids, are. So on your periodic table, or on the one that I posted on Blackboard, you'll see that there's kind of this bold zigzag line right here on your periodic table. So that bold zigzag line, that's used to separate the periodic table from the nonmetals and the metals. So everything to the right of that zigzag line are nonmetals in blue. Everything to the left of that zigzag line are metals in this green color here. Now the exception to that is hydrogen. Hydrogen's hanging out over here on top of these alkali metals, but it's not a metal, it's actually a nonmetal. So notice it's in blue. So that's the exception here. Now I have a third color, purple, and that is representing the semi-metals or the metalloids. So anything touching this zigzag line is going to be a semi-metal. With, of course, there's always an exception of aluminum. Notice aluminum is touching the zigzag line, but it's clearly in green, it is a metal. So you can tell most of the periodic table is made up of metals, because we have this whole block here that I didn't write the elements in. These are the transition metals. There's about 40 of them that I didn't write, or 30 of them I should say. So, quick review. So we looked at the organization of the periodic table last week, including where the metals, nonmetals, and semi-metals were, but we also looked at group names. So this first column here, with the exception of hydrogen, are called the alkali metals. The second group, beryllium, magnesium, calcium, strontium, and barium, these are the alkaline earth metals. This big block in the center, we just call those the transition metals. And then we don't have any special names for group 13, 14, 15, or 16. So there's no special names for those guys because if you'll look, they're made up of nonmetals, metalloids, and metals. So since they have such a variety in their group, they don't have common characteristics. So they aren't given a common name. But when we get way over to group 17, fluorine, chlorine, bromine, and iodine, this group is called the halogens. I should write that up here instead. Because notice they're all nonmetals and they have similar properties, so halogens. And then this last group, these are the noble gases. That's what everybody wants to be. All the main group elements want to be a noble gas. And we'll talk about that with the octet rule in the PowerPoints and then a little bit next class as well. But what we're going to do is we're going to use our knowledge of where the nonmetals, metals, and semi-metals are to figure out if a compound is covalent or ionic. So let's look at the definitions of a covalent and ionic, and then we will look at the rules for naming them and practice naming a few. So for a covalent compound, so with covalent, this is where we're sharing electrons. Because when we talk about compounds are two or more elements combined. Okay, so an example of a covalent compound would be CO2. Because they're sharing electrons, so we have carbon atoms and oxygen atoms coming close together and sharing their electrons. So there's no charges involved. Now, how do I know it's covalent based off of this chemical formula? Is because I look at what carbon and oxygen are. So finding them on the periodic table, they're both in blue. They're both nonmetals. And by definition, a covalent compound is composed of two or more nonmetals. The other way you can form a covalent compound is between a semi-metal and a nonmetal. But you're never going to see a metal in a covalent compound. Okay, so it's all nonmetals or semi-metals. So that's how you identify given the chemical formula. For ionic compounds, now this is where metals are involved. So for ionic compounds, we're transferring electrons. What that means is one of the elements in the compound is giving away electrons, the other element in the compound is accepting or taking those electrons. Now remember, electrons are negatively charged. So we're playing with the charges. So when we take away electrons, what happens is we're taking away a negative charge and we're going to form a positively charged ion. If we're given, or one of the elements takes an extra electron, accepts an electron, it's going to have an extra negative charge. So we call these charged components ions, and we have two different names for them. We have a cation and an anion. So the reason we have different names is because one of these represents the positive when electrons are lost, and the other represents the negative when the electrons are gained. So how do you remember which is which? For cations, you can use the name itself as a mnemonic device. So I see A, and then this T can be positive, a plus sign, a positive ion. So a cation is the positive ion formation. And we're always going to see the metals form the cations. So metals are always going to have a positive charge because metals like to donate electrons. They like to give their electrons away. So if they give those negative electrons away, they form a positive charge because they lost the negatively charged electrons. Now for the anion, you can use this as a mnemonic device as well. A, N for negative, and then ion. So the anion is the negative ion portion of the ionic compound. These are always going to be with nonmetals because nonmetals like to gain electrons. They like to take them. So the example I have here is sulfur, which is a nonmetal, and it has a negative charge on it. So this compound would look like this. This would be the chemical formula if magnesium and sulfur formed a compound. Because magnesium is giving 2 electrons away to form a +2 charge. And it gave those 2 electrons to sulfur, making sulfur have a -2 charge. So with ionic compounds, we're going to see metals with nonmetals. Because we learned in previous chapters, opposites attract. So we always want to see a positive cation combining to make a compound with a negative anion. So we're never going to see 2 positive ions forming a compound or 2 negative ions forming a compound. It's always going to be a positive with a negative. All right, let's look at naming now. So the reason we're looking at how to figure out if it's covalent or ionic is because there's different ways of naming it depending upon what type of compound it is. So you have to first be able to apply these definitions and figure out if it's covalent or ionic before you can go ahead and apply the naming rules. So we're going to start with covalent compounds where electrons are shared. So we're looking at just this section of the periodic table with the nonmetals and the semimetals. So the rules for naming covalent compounds is, first off, we're going to have prefixes. So we'll have a prefix, and then we'll write the element name, or I should say first element. And then another prefix, the second element, and an IDE ending. Okay, so what do I mean by prefixes? Well, it's easiest to explain when we can apply it to a problem. So let me find an example here. Okay. So say we wanted to name this guy. So this is a chemical formula of a compound. So, to figure out the type of compound, we look up the elements, nitrogen and sulfur. Nitrogen's a nonmetal, sulfur's a nonmetal. So we can identify it as covalent since they're both nonmetals. Electrons are being shared. So once we know it's covalent, we're going to use prefixes, and we're also going to add an IDE ending to the second element present. So what are the prefixes for? The prefixes tell us how many atoms of each are present. So So notice this 2 that comes after nitrogen, that's saying there are 2 nitrogen atoms. So we're going to use a prefix to indicate that there are 2 of them. So our prefixes, we're going to list them here, are mono, di, tri, tetra, penta, hexa, heptum, run out of room, octa, and nona is the last one. And that one's hard to see, but we don't really see that one very often. And I have a table of these prefixes in the PowerPoints as well. I wanted to copy it down from there. So if I wanted to name this compound, I need to start with a prefix to indicate how many atoms of that first element there are. So since I have a 2 after the nitrogen, that means I want to start naming this compound by using the prefix di, because there are 2 of them. So it's di, and then I use the first element name straight from the periodic table. So the element symbol N leads me to nitrogen. So it's di, and then nitrogen, just how it's spelled on the periodic table. No changes. And then now I need to name the second element that's present, the S. I start, once again, with a prefix indicating how many sulfur atoms there are. Now there's no subscript after the sulfur, so I assume that there's just one of them. So I use the prefix that corresponds with the 1, and that's mono. So it's going to be, I'm going to start with mono, the prefix, and then I'm going to write the second element's name, but I'm going to add an IDE ending to it. Okay? So I'm not going to write sulfur. Instead, I'm going to write sulfide, that IDE ending. And you only put the IDE ending on the second element present in the chemical formula. The first element present, just the prefix and the element name. So this is the correct name for that compound, dinitrogen monosulfide. Let's try another one. So it's a covalent compound, but if you're not sure, you just find both those elements on the periodic table and confirm that they're both nonmetals, phosphorus and bromine. Yes, they're both blue. So now you can name it using prefixes and the IDE ending on the second element. So starting with P, phosphorus. How many are there? 2. That's what the 2 is there for. So we find the prefix corresponding to 2, and it is di. So we have di, and then phosphorus stays the same. We don't make any changes to it because it's the first element present. The second element present, start with the prefix indicating how many of each. So we have a 4 here, so the prefix for 4, tetra. And then bromine, we're not going to write bromine, I-N-E. We're going to add or change that I-N-E to an I-D-E. So it's going to be, instead of bromine, it's going to be bromide. Make a little list over here too, how the nonmetals change with their IDE endings. So carbon becomes carbide. Nitrogen's kind of a hard one. Some people like to say it becomes nitrogenide. That's wrong. It just becomes nitride. So shorten it up a little bit. Oxygen becomes oxide. We've already seen sulfur becomes sulfide. Phosphorus becomes phosphide. What else do we have? And then all the halogens, fluorine, chlorine, bromine, iodine, they're all very similar. The I-N-E that they end with just becomes IDE. So instead of bromine, it's bromide. Instead of chlorine, it's chloride. Fluorine, fluoride. Those ones aren't too bad. It's these two that usually trick people the most. Because you take off this whole ending and add the ID. All right, let's try another one. So now let's look at an exception to the rule. There's always exceptions to the rule, right? So let's do CO. Now, if I was going to name this guy, it's covalent because we have carbon, we have oxygen. They're both nonmetals. Now it tells me that I need to start with the prefix of the first element. So in this case, there's only one carbon. So I should start with mono. But here's the exception. The first element present, if there's only one, you do not use a prefix. So that's the only time you don't use a prefix, is when it's the first element and there's only one of them. So I'm not going to write monocarbon. I'm not going to use a prefix. I'm just going to write carbon. Now the second element, oxygen, there's only one of them. But just like up here, sulfur, there's only one. We did use the mono because it's the second element present. So I am going to write mono, and then I'll change oxygen using my system over there. Oxygen with the ID ending becomes box I. Now, why didn't I use the mono? It's just a rule that they applied to covalent compounds. There's no real trick about it. But if you think about it, you've heard of carbon monoxide before, but you've never heard of monocarbon monoxide. So it's a common name that you've probably heard. Same with CO2. CO2 is carbon, 2 oxygens this time, so dioxide. That's what we breathe out every day. And they just don't include the mono because there's only one element present. So if it's the first element in that chemical formula and there's only one, we do not put the prefix. So that's the only exception. Otherwise, you put prefixes for covalent compounds every time. All right, let's look at going the other direction now. So we've looked at, okay, you're given the chemical formula, tell me what the name is. Now we're going to go the opposite way. I'm going to give the name and we're going to come up with the chemical formula. These are still sticking with covalent compounds. So let's look. Dioxide. That's first. A couple of them. Diboron. One more. Fluoride is always a weird one. Okay, so I have 3 different names of 3 different compounds. I know they're covalent because we're using prefixes. As we'll see when we look at ionic, when we name ionic compounds, we don't use prefixes at all. So if you see a prefix in a chemical name, it's definitely covalent. You can also confirm it's covalent because if you find nitrogen and oxygen, they're both nonmetals. So you figure it out either way. So how do I change this into a chemical formula? Well, you look up the names for nitrogen and oxygen, because oxide is just the IDE form of oxygen, and you find their chemical symbols. So we have an N for nitrogen and an O for oxygen. So I'm going to have an N and I'm going to have an O. Now for the subscripts, what I'm going to write here, I'm going to use the prefixes for that. Okay, so this di tells me that I have 2 nitrogens. So I'm going to put a 2 after the N to indicate that. Same for the oxygen. Look at its prefix. That'll tell you how many there are. In this case, tri, which is 3. So we're going to put a 3 after the oxygen. So this is the chemical formula that goes with that name. Dinitrogen trioxide. All right, let's try the next one. We have di again, diboron this time, and then tetrahydride. That's one I forgot over here. That's a hard one sometimes too, because it's hydrogen. That's hydride. So, figure out what elements you have. Boron, letter B, it's a semimetal. Tetra, that's the prefix, so we have hydride. Hydride is the IDE form of hydrogen. So finding hydrogen on the periodic table, it's represented by the chemical symbol H. Now we use the prefixes to write our numbers. Di means 2, so we have 2 borons. Tetra means 4, so we put a 4 after the H. All right, now I want to do this last one just because you'll notice the first element, name, oxygen, doesn't have a prefix. So if it doesn't have a prefix, how many do you think there are? Just one, right? If this absence means there's just one of them. So oxygen is just O, and since there's no prefix, we know there's just one of them, so we don't need to write anything after it. Now the second part, fluoride, that's the IDE version of fluorine, this halogen here. So I'm going to write F for the symbol. And this one does have a prefix. It says di. So di, once again, is 2. So OF2 would be the correct chemical formula going with that name. So the covalent compounds are kind of nice, a little bit more straightforward, just because we're looking at such a small section of the periodic table. We're going to look at naming ionic compounds next, which is the whole periodic table, because we're bringing the metals into the game. So to name ionic compounds, we are not using prefixes anymore. Okay, so no prefixes for ionic. You may even erase these. We are, however, still using the IDE endings on the second element present. So ionic, remember these were ions, the cations, the positively charged, and the anions, the negatively charged. We're going to start with just the simplest form, which is a metal with a nonmetal. So when you name ionic compounds, when you have a metal and a nonmetal, no prefixes. So how we're going to name it is we're going to do the first element name present in the chemical formula, and then the second element will have that IDE ending, just like before. So we basically just took the prefixes out, we're doing everything else the same. So let's look at some examples. GBR, Li2S, GBR2. All right? So to name these, we have Na. It's one of the alkali metals. It's actually sodium. So you'd have to look up the symbol probably to figure out the name for that one. So notice the metals always come first as well. So it's always the metal first and then the non-metal comes second. So Na is sodium, so I just write sodium, no changes to it, no prefixes. The second part of this chemical formula is Br. Br is the non-metal portion, a halogen in this case. So Br is bromine, but we want to add an IDE ending. So bromine is going to become bromide. There's only one bromine, but that doesn't matter when we name it. We're not going to put monobromide because we're now doing ionic compounds. All right. Looking at the next one. So notice there's 2 lithiums, but we're not using prefixes. We're not going to write di. We're just going to look up the Li, lithium, alkali metal, and name it just how it's written on the periodic table. So it's just lithium. S, the nonmetal portion, right here, S is sulfur, so we just change that with an IDE ending, add one. So instead of sulfur, sulfide. So these are a little bit nicer names, you don't have to look up the prefixes. It's coming up with the chemical formulas that's going to be a little bit hard. We'll look at that here in a second. So last but not least on this list, we have Mg, alkaline earth metal, magnesium here. And then once again, bromine, just like here. There's two bromines, but we still name it the same way because we're not using prefixes. So bromine just becomes bromide. So magnesium bromide. So now for the hard part. What if you're given the name and you need to come up with the chemical formula? Because notice our names no longer have prefixes, and the prefixes told us how many of each. So we can't use the prefixes to figure out how many atoms of each. Instead, we're going to have to use their charges, those cations and anions. Okay, so I'm going to write down some examples, and then I'll show you on the periodic table how we predict charges. So here we have we're going to take magnesium oxide. Let's do chloride. Sure. So here's two names of two ionic compounds. Notice no prefixes, and then we have a metal with a non-metal. So how do we come up with their chemical formulas? Okay, I said we need to know their charges. Remember, ionic compounds, we have ions that are forming. So we can use the periodic table to figure out what charge the elements have based off of what group they're in. So alkali metals, group 1. I said metals like to lose electrons. Metals are always going to be the cation, the positive charge. For the alkali metals, this group forms a +1 charge in an ionic compound. So lithium, sodium, potassium, rubidium, cesium, anytime I see any of those elements in an ionic compound, I know that its charge is +1 every time. Alkaline earth metals are always a +2. Once again, they're metals. They lose electrons to become a positive charge. Aluminum, over here, is a +3. Kind of seeing a trend here. +1, +2, +3. So are gallium and indium. Those are +3s as well. But next, we get into the non-metals now, right? We're into the blues. And the non-metals like to gain electrons. So the non-metals are going to be negatively charged. So those charges go as follow. Let me erase this so we can see. So the noble gases, these are the stable ones. They don't react, they don't form ions. Because they are happy, they have 8 valence electrons. So they're neutral, essentially. We'll say 0. Halogens form a -1 charge because they like to gain 1 electron. Oxygen on down, oxygen, sulfur, selenium, like to be -2. And then nitrogen, phosphorus, arsenic, like to be -3. So the metals gain 1, 2, 3. Lose. The non-metals gain the electrons, -1, -2, -3. So you can even just write that on your periodic table so that when you get a name and have to come up with a chemical formula, you can just refer directly. So, to name this guy, we're going to use the charges to figure it out. So we have magnesium, Mg, right here. It's an alkaline earth metal. So start by finding the symbol and then writing the charge. So magnesium's an alkaline earth metal, and it's always going to form a +2. Now oxide, that's just oxygen. So finding oxygen, it's right here in group 16, its charge is -2. So how do I know what that formula looks like? The goal is it needs to be a neutral compound overall. right? When we write these ionic compounds, there's no charge on the outside of the compound. It's neutral. So what that means is I need the charges to cancel. In this case, I have a +2 and a -2. So if I added +2 plus a -2, that would equal 0. They cancel each other out. So what this means is I need just one of each. So my chemical formula, I just need 1 magnesium and 1 oxygen. So that's it, MgO. So that one worked out nicely because they canceled. We didn't have to add any extras. The next one's not going to be quite so nice, so we'll kind of see what we do when they don't cancel. So with aluminum chloride, we have aluminum right here, group 13. We said since it's a metal, it's going to form a positive charge, in this case +3. So write the symbol with the charge. Now it's attached to chlorine, a halogen. So all the halogens in group 17 here have a -1 charge. So I'm going to write Cl, the symbol, with a -1 charge. Now this time the charges aren't canceling. So what that means is I'm going to need more than just one of each. Because if I had just one aluminum and one chlorine, I'm going to have a positive charge left over. Right? If I take a +3 and add a -1 to it, I'm going to have a +2. And I don't want that. I want it to be neutral. So what I need to do is I need to add more chlorines. How many more? 2 more to be exact. Because if I have 3 total chlorines, the total of my anions, of my negative charges now, is going to be -3. Now that -3 will cancel out the +3 that I have on this aluminum. So that means I need 1 aluminum and 3 chlorines to make it neutral. Another way to do this, a quick way to do this, is called the crisscross method, is where you take the number, not the charge, but the number on the first atom, and it becomes the subscript on the second. So it's saying I need 3 chlorines and 1 aluminum. So you're crossing that. I'm not bringing the charge, but just the number. So AlCl3, this is the correct chemical formula because I need 3 chlorines to have a total -3 charge to cancel out that +3 on aluminum. And to figure it out that shortcut way, you just swap the charges and make them the subscripts. Let's try another one. All of these have like polyatomics in it. We haven't talked about polyatomics yet. So let's try sodium. Oxygen. Sure. So, no prefixes, so it tells me that it is definitely ionic. I have a metal and a non-metal, because the metal always comes first, and the metal always has a positive charge. So looking up sodium on the periodic table, to name it, you immediately go find these 2 elements on the periodic table, write down their symbols and their charge. So sodium, I'm going to find the symbol. It's Na, and since it's an alkali metal, it's got a +1 charge. So I'm going to write Na with a +1. Na +1. The second half, phos5. Okay, this is just phosphorus, right? So looking at phosphorus on the periodic table, it's a P, and based off what group it's in, I know the charge, -3. So I'm going to write P with a -3 charge. Now, the charges don't cancel, so I need more than one of each. So I need to do my crisscross method. What that means is I need to take this 3, and it becomes the subscript on sodium. So I need 3 sodiums, and I'll take this 1, and that becomes the subscript on phosphorus. So it's going to be Na3, and then P. And there's just one of them, so I don't need to write the number. So coming up with the chemical formulas for ionics is a little bit more difficult because you have to use the symbols and their charges to figure out your subscripts. So what we're going to look at in the next video, the next class, is we're going to continue with ionic. We're just going to add some more layers on it. So we're going to look at polyatomic ions, and we're also going to look at the transition metals. Because notice we haven't named any compounds, ionic compounds, using this middle section. Because this gets very difficult because we don't know the charges on these. We know the charges on the alkaline earth metals, but the charges on the transition metals are tricky. So those get to be a little bit more difficult. So we'll cover that in the next video.